In this video, we learned to calculate the normal force and parallel and perpendicular weight components on an inclined plane, and then we apply these ideas to an example. So in our picture, we have a block of mass m on an incline tilted at an angle of theta. To start solving the problem, we want to get the force vectors into the diagram first. So first we have the weight, or force of gravity, pointing straight down as always. And remember, this vector has a magnitude of mg, and I'll post a link to the video where that was first derived. Next, we know the surface exerts a normal force perpendicular to the surface, and that normal force is just right to guarantee that the net force perpendicular to the surface is 0. In other words, the normal force is responsible for keeping the block moving on the surface instead of sinking into the surface or jumping off of it. Now, the normal force is perpendicular to the ramp, and any acceleration is going to be parallel to the ramp. So the natural coordinate system here is tilted. Our strategy is to analyze forces in the parallel and perpendicular directions to the ramp surface, applying Newton's second law in each direction. This brings up a problem. How do we find the components of the weight vector parallel and perpendicular to the ramp? We can see that part of the weight vector points perpendicular to the ramp, and part of the weight vector points parallel and down the ramp. But we need to find this angle in order to use trigonometry to get those components. Note that in our force analysis, we usually translate this parallel piece and attach it to the mass to emphasize that it's acting on the mass. Now, there happens to be a way to find this angle without using any trigonometry. So to illustrate, we start with our ramp in a horizontal position. We're going to let our coordinate axes tilt with the ramp, and we keep track of this angle as the plane rises to its final angle. Now we just translate our coordinate axes to the location of the mass. So we see that our angle of incline and our angle between the vertical and perpendicular are equal. And now we can get back to solving the problem. So we put in our weight vector, which always points down and always has a magnitude of mg. And we want to decompose this into parallel and perpendicular components. Well, now we can see that the perpendicular component is just the adjacent side of a right triangle whose hypotenuse is mg. So that's given by mg cosine theta. The parallel component, well, that's given by the opposite side of the right triangle. So we get mg sine theta for that. And again, we usually translate that parallel component and attach it to the mass to emphasize that it's acting on the mass. Finally, we get the normal force into the picture. And recalling that the normal force will be whatever it has to be in order to make the perpendicular forces sum to 0, we see that it has to exactly cancel the perpendicular force of gravity, which has a magnitude of mg cosine theta. So that normal force has a magnitude of mg cosine theta as well. Now that we've figured out all the forces and components on an inclined plane, we're ready to apply this to an example. So in our example, we have a block of mass 2 kilograms sitting on an inclined plane elevated at an angle of 35 degrees. And we're told the block is initially held in place with a string that's parallel to the ramp surface. And then the string is cut, allowing the block to accelerate down the ramp. In part A, we want the initial tension in the string. In part B, the normal force on the block. And in part C, the acceleration down the ramp when the string is cut. So to prepare for the force analysis, we put in a set of perpendicular and parallel axes. And like any dynamics problem, we start by putting in all the forces and decomposing them into components. First, we put in the weight vector, and that has a magnitude of mg. And we can just go ahead and plug the numbers in here. M is 2, g is about 9.8. So the magnitude of this weight is 19.6 newtons. Next, we put in the components of the weight vector. And again, we note that the angle of incline for the ramp is the same as this angle between the vertical and the perpendicular. And that means our perpendicular component is an mg cosine of 35. That's 19.6 cosine 35, which gives us a magnitude of about 16.1 newtons for the perpendicular component. Our parallel component has already been translated to be attached to the mass itself. That's going to be an mg sine 35. So 19.6 sine 35, and that's approximately 11.2 newtons. Next, we put our normal force into the diagram, and we'll get back to that when we talk about part B in the problem. And then our final force vector here is the tension pulling up and parallel to the ramp. Now to solve the problem, we're just applying Newton's second law in the parallel and perpendicular directions. And part A is a parallel question. I'm asked for the tension in the string, and that tension is exerted in the parallel direction. And the block isn't moving at all because it's held in place by this string. So qualitatively, we can just say that the forces balance in the parallel direction. But if we want to get a little more formal with it, what we're looking at is F net along the parallel axis. So I'll write it as F net parallel. That's equal to MA in the parallel direction. And the acceleration is 0 because this block is stationary. So that means the sum of the parallel forces is going to vanish. Now up the ramp, we'll go ahead and call that positive, and down the ramp, we'll call that negative. So if I write in my sum of forces, that's T as a positive quantity, and then minus mg sine of theta, or sine of 35, because it points down the ramp, and that has to be equal to 0. This means that T is equal to mg sine theta, or mg sine 35, which we already computed, so T is 11.2 newtons, guaranteeing that that block doesn't slide up or down the ramp. In part B, we're asked for the normal force on the block. And again, there's an informal approach to this. I can say the block is stationary, so all the perpendicular forces must balance. So I can immediately tell the normal force is equal in magnitude to the perpendicular component of gravity. But to be a little more formal about it, we're actually applying Newton's second law in the perpendicular direction. And because the block has no acceleration in that direction, F net in the perpendicular direction, again, vanishes. We'll count up and away from the ramp as positive, and then down and toward the ramp as negative. So I get n minus mg cosine theta, or cosine 35 degrees, is equal to 0. This means our normal force is equal to mg cosine 35. But we already computed that and put it in the diagram. So we can say our normal force is 16.1 newtons. Finally, we want the acceleration down the ramp when the string is cut. So the physics of the problem has changed here, and we want to get rid of the string and that tension pulling up the ramp. Now the block is going to accelerate down the ramp because I have a net force in that parallel direction pointing down the ramp. And we have a choice here on which way we define the positive direction. We can start over and say, okay, now let's call down the ramp positive. And that makes the parallel component of the force of gravity into a positive number and the acceleration into a positive number, and it's just nicer that way. If you like, you can try it with up the ramp being positive, and your answer for the acceleration will be the same, just with a minus sign in front. And again, we're really applying Newton's second law. So I can say F net in the parallel direction, again counting down the ramp as positive, is equal to mass times the acceleration in the parallel direction. Well, F net is just 11.2 newtons. It's the only force acting parallel now that the string is gone. And our mass is 2 kilograms. And the only unknown here is the parallel acceleration. Dividing both sides by 2 kilograms, we obtain a parallel acceleration of 5.6 meters per second squared. And we're done. If you enjoyed this video, or at least found it useful, check out another one by clicking one of the links on the left, or click the Zach's Lab logo on the right to explore dozens of physics and math playlists. As always, you can leave your questions, comments, and requests in the comments section below, and I'll get back to you within 24 hours. Thanks for watching Zach's Lab, and best of luck on your math and physics journey.